to me, wait, because the outside committee hasn't come yet. I'm waiting for them. I'm sorry.
Where's everybody else?
Oh, the wait is over there, but the outside committee hasn't come yet. So we said we.
Third being.
But I don't know how many times I asked the wait. He didn't say. He's not sure yet.
Oh, Oscar hasn't come.
Yeah.
Okay. Hello. Welcome back. Hi. Okay, sorry for the delay, everyone. Our outside member just arrived. Okay, so without further delay.
Enough inside members, though.
Where's Yanni? Wait, he was here. All right. Our inside member will now arrive.
Hello. How are you? Good. How are you? Good.
All right, I found him. He's at the printer. All right, we're going to go ahead and start. He's coming in.
Okay.
All right, so this is the final defense for my student Ying Liu. She's going to talk to us and tell everyone about her work on robustness and ad hoc networks.
Yeah.
We're going to ask you just to accelerate a little bit because we lost a little time, but don't worry.
Okay.
You know, we'll push you anyway.
Yeah.
And Yanni will be here in 30 seconds. Once he comes in, sits down, you go through your own introduction. But this ought to be a pretty interesting talk. There's a mix of network simulation stuff and also mathematical modeling.
Yeah. Thank you very much, Professor Wayne Trippi, for your kind introduction.
Wait till Yanni arrives.
So you're still working on wireless security in general area?
Those of you who don't know Oscar, she was an ex-WinLab, now Nokia person.
Oh, Nokia.
Nokia bought Alcatel.
Oh, yeah.
Sorry, I didn't register. Right.
All right. You go ahead and start now.
Okay. First, thank you all for coming to my PhD defense. I hope you all will enjoy my thesis, my presentation. And my name is Ying Liu. I'm a PhD student from the Department of Electrical and Computer Engineering. And my topic is robustness in ad hoc networks, which is under supervision by Professor Wei Trippi. So why we study robustness? Robustness is required by most of today's networks, such as IoT networks, vehicular networks, and military networks. Robustness studies how a wireless network is connected with some of its components crashes, how network connectivity relates to a network's robustness. As we know, a better network connectivity usually means stronger ability to recover from faults and attack. So I'm trying to study connectivity in order to improve robustness. So what factors affect connectivity? One is natural disturbances, which includes passive interference, and another is adversarial disturbances, which includes jamming attack. This is so the focus of my thesis is, in general, it studies how networks are made more robust with better connectivity to minimize disturbances. I deal with this problem by the following 4 aspects. One is overlay design for network robustness, which deals with natural disturbances. And the second one is discover adversarials and design topology for robust networks, which deals with adversarial disturbances. And the third one is understanding connectivity with interference, which both comes from natural and adversary disturbances. And the last one is to defend against unknown attack strategies. This is an overview of my thesis. Around the topic of connectivity, I did 5 projects. I will give brief review on the first 2 projects since I already presented it in my PhD proposal defense. And then I will give more details on the last 2 projects, which is my rest of the work and has some new results. So the first project is distance-aware overlay routing. The motivation behind this project is to design an overlay routing to solve backtracking problem and reduce latency. My solution is to build an agency matrix with nearest k-class heads. As we can see in this picture, the class head I is surrounded by n-class head, and it will pick k-class head, the closest peak k-class head in terms of distance, and form an agency linked list based on this k-class head. And after agency linked list is built, then we can get the overlay logical topology, and the class head I can find the shortest path based on this logical topology. And then this shortest path is handed down to the underlayer AODV routing, and AODV routing will route the packets hop by hop to its destination. So this is a simulation result. As we can see in the upper picture, the pink line corresponding to AODV routing, which is the ideal case we want to achieve, and it does not consider the overlay routing. And the green line is corresponding to our algorithm, and the red line and the yellow line corresponding to CORD routing protocol. And as we can see, our algorithm gives much fewer average hops than CORD routing. And also the performance of a CORD had a large variance compared to our algorithm. This large variance reveals the general behavior associated with the backtracking in CORD selected paths, since CORD randomly places class head in the CORD ring and doesn't consider the geographic location of class heads. And also in the bottom picture, we can see with minimum hop class head, our algorithm had a low failure transmission probability compared to CORD, which shows in this pink line. And this is the second project I was doing.
2 questions. I don't That's why, so sorry. Why is the AODV, as you said, ideal baseline? And what are you trying to optimize?
AODV is because it doesn't consider the overlay, and for each routing path, it has to go first to the class head, then down to the lower nodes, the network nodes. So the AODV doesn't let the path go to the class head first. It directly route the packet through the underlayer nodes.
Okay, but I think I heard you say that's the ideal baseline, so why is it like DIMO the baseline? Why is AODV the baseline?
Because in fact we cannot achieve AODV, but because AODV didn't route packet through the class head, so it reduces some of length to the class head, some length of a path to the class head. So yeah, it directly.
And what were you trying to optimize?
I'm trying to reduce the length of a path, the routing path. And here, because we have to go through the overlay routing, because the upper layer application needs some overlay routing in order to find the file data, the data file. So it has to go over for example, the gateway first, then go back to the, for example, node in the edge of the network and route the path. Yeah.
So go back one slide.
Back one slide.
Yeah.
Okay. Yeah. So here you can see.
Layer 3 is fixed. It's AODV.
Yeah. So for AODV, it directly route the packet from source to destination. It does not go through this class head. So when they route to the class head, it adds the number of hops. Yeah. And the second project I was doing, I did is Jammer localization. The motivation behind of this project is to localize an ongoing attack. The jammer near the target node continuously broadcasts the format compliant packets, which blocks the target node communications to other legitimate node. The technique I use is reinforcement learning. That is, each node learns the minimum expected packet loss ratio among its neighbors. As we can see in this picture, Q-learning information is exchanged among neighbors through one hop and by routing layers. And this is a simulation result, and we can see adversary trying to block the communications of a legitimate node. And at the same time, he injects false information into the network in order to confuse Q-learning detection. As we can see, the arrows that represented an optimal direction choice of legitimate node all points to the potential jammer position. And also Q-learning can find either the legitimate node that is closest to the jammer here and also find the exact position of a jammer. And the following slides is my recent work. I will allocate more time to it. And so the outline for the following discussion topic is one, I will provide the previous work, and the second, I will provide a theoretical understanding of connectivity with existence of interference, followed by 2 case studies. And the third one, I will provide a defense strategy for repeated connectivity jamming game in ad hoc networks. And the last one is I will demonstrate how to use multi-agent reinforcement learning to mitigate congestion. So let's come to the previous work on connectivity study. So what is the commonly used metrics to study connectivity? The first one is node degree, which describes the probability distribution of node degree in a large-scale network, such as internet social network and citation networks. And the second one is mean cut metric, which gives the lower bound on the minimum number of edges needed to separate node. And the third one is algebraic connectivity, which comes from graph theory and is the second smallest eigenvalue of Laplacian matrix. And the last one is vortex and edge connectivity, which demonstrate how many independent paths between two nodes. So as we can see, there are many scientific papers uses metrics to measure the connectivity, and some ways to increase connectivity by adding edges, by adding set of relay nodes, and reposition nodes in the network, and also by adjusting nodes power. However, what they are missing in common is they seldomly consider the interference and no combination between throughput and connectivity, and no consideration of parameters in physical layers such as transmission power, geographic location, and natural noise. So to supplement the lack of studying connectivity, I first try to theoretically understanding of connectivity under interference, and this gives us a guidance to design a real protocol. So as we know, interference adds uncertainty to a network by both natural and artificial reasons. As we can see in this picture, A and B are communicating with each other, and D is trying to increase its transmission power in order to build communication between A and B. And with transmission power increases, D's transmission power breaks the communication between A and B. So the question is whether the throughput increases or decreases, whether the connectivity increases or decreases. So in order to understand this question, I come up with two approaches to measure impact of connectivity. One is called throughput connectivity. The other is called weighted throughput connectivity. And these two measurements all uses the physical metrics that consider interference. And I applied these measurements to the power allocation cases in order to minimize interference to achieve a reliable connectivity. So how to consider interference in a graph? As we know, throughput transmitted between two nodes can be expressed by Shannon theory. That is, if a signal to interference and the noise ratio is less than a receiving threshold, then there will be no information bits can be transmitted on the link between two nodes. And if the SNR is larger than the threshold, then the information bits that transmitted equals to the Shannon equation. And the benefit here we use SNR is that it automatically considers interference between legitimate users as well as other physical parameters such as the transmission power and the distance and the natural noise. My definition of existence of a link between two nodes is as follows. If there are throughput on both directions of a link between two nodes, then there will be an edge in the topology graph. Otherwise, there will be no edge between two nodes in a topology graph. And here I only consider the symmetric link, since in the routing layer, the routing protocol only consider the symmetric link. And also, this definition can be applied to full duplex communications. And also, in order to extend the throughput connectivity, I assign the weight to each link between two nodes, which describes how many bits information can be transmitted on the link, and its value equals to the sum of the total throughput on the two directions. So by applying throughput connectivity and weighted throughput connectivity into the Laplacian matrix, we got the following equations, and we can see Laplacian matrix maintains the symmetrical property, and this is a good feature because it corresponding to the semi-definite matrix. Then we can calculate a field value by the following equations through the above Laplacian matrix, and we can see y is an eigenvector of a Laplacian matrix, and it does not equal to all one vectors. this constraint forces the optimization equations to give us the second smallest eigenvalue of Laplacian matrix, and which is also the algebraic connectivity in the graph theory. And based on the graph theory, we know the larger the field value, this algebraic connectivity, the more connected the network is. So in order to check the correctness of my measurement for connectivity under interference, I asked one node to selfishly increase its transmission power in these 5 nodes networks. And only node 5 increases its transmission power, and node 2 and node 3 and node 4 maintains the same power. And we want to check the dynamics of throughput connectivity and the weighted throughput connectivity, as we can see in the right picture. As the transmission power increases, the throughput connectivity first increases, then decreases. It can prove the phenomenon that the picture shows in the previous slides, that the interference adds uncertainty on the connectivity. And moreover, with a larger threshold epsilon, we can see the throughput connectivity even becomes 0 after it passes some threshold. It means the network is totally separated, and it is totally disconnected. Also, the same property shows for the weighted throughput connectivity. So we can conclude here is that there's no consistent increase on connectivity if we only ask one node selfishly increase its transmission power. So this also gives us a hint that whether we can ask a node to collaboratively adjust its transmission power in order to improve connectivity. So let's check our result. So the goal here is that nodes in a network cooperatively adjust their transmission powers to limit interference. I formulate this problem into the mathematical optimization show as following, and we can see the minimized part is trying to calculate the field value, and the maximized part is trying to maximize the field value by allocate the optimal transmission power among nodes. And this optimization also subject to a constraint, which is the sum of individual transmission power should equals to the total network power. So I searched several literatures. I found that this max-min optimization can be transformed into the following semi-definite programming problem. Why it is a semi-definite? As we discussed before, because Laplacian matrix is symmetric, so it is semi-definite. And also the identity matrix is a semi-definite. There are many MATLAB codes that can solve the semi-definite programming problems. So I applied one of them, and I get the following numerical results. Compares to the previous inconsistent increase on the node on the connectivity, we can see in the picture both throughput connectivity and weighted throughput connectivity becomes non-decreasing. And especially for the large transmission power, we can see it maintains the network connectivity. That means the throughput connectivity, the value doesn't becomes 0. And so the network is totally connected. And also, the second observation we found in our simulation is that the jump in the throughput connectivity indicates at least a new link is added to a network. Also, an increase on weighted throughput connectivity demonstrates a raise on successful transmission of information. So let's go to the second case study, which deals with the real protocol design by allocating transmission power in physical layer to adapt topology. So as previous observation, we found no degrees increases with radial range through increasing power. However, the number of reachable source and destination pairs has reached a bottleneck. So the conclusion is we need to increase power according to network connectivity under interference. So my idea is we can extract topology through routing protocol that already considers connectivity subjected to interference. After we did a topology extraction, we can select k connectivity inference nodes and increase their transmission power until the level of connectivity reach a threshold. And this is a method how we get topology information from optimized link state routing protocol. And we can see hello message can give us 1 and 2 half neighbors, and the TC message can give us more than 2 half neighbors link status. And after we get those connection status, we can form an adjacency matrix and get the network topology. Based on this network topology, and we can find the nodes with most inferential connectivity, and by following procedure. First, we can remove each node I from a graph G, and we can get a corresponding algebraic connectivity, also the physical value lambda I, for the remaining graph by removing node I, and then we will rank those lambda I into a descending order. Then the k nodes with most inference on connectivity corresponding to the first k largest lambda I. So in order to validate our algorithm, we did a simulation in a scenario that attacker can simultaneously block communication from 1 node to 5 nodes. Here we can see our simulation, our algorithm reduces the average number of hops by at least 50%, and also cut the mean delay by at least 60%, and improve mean throughput by more than 2.5 times. And we also consider the mobility scenarios, and our algorithm improve throughput and mean throughput and delay by at least 50% when speed is less than 30 meters per second. Of course, our algorithm cannot satisfy all cases, and so the improvements on average hops and throughput decrease with speed also, and this is very common sense. And the fourth project I did was to understand the throughput connectivity jamming game in ad hoc networks. So what is the objective to study jamming game on connectivity? One is to model and understand the impact of interference attack on connectivity. Another one is to provide a defense strategy. So the goals of a jammer and a scanner is a jammer tries to jeopardize most connectivity, influence the node, and block its communication through interference. And the scanner uses some form of detector to detect a signal of a jammer. If the jammer stays longer on the node, it increases his chance to be caught. And while at the same time, a scanner tries to force jammer to choose costly options in order to conduct its jamming attack. So this here is a jammer's normal attacker's normal routine. As it is as follows: if jammer and the scanner were on the same node, because the scanner is simultaneously scan the target node, the jammer would switch to the hiding mode. If he was caught, he would stop his attack. If he was not caught, he will continue his attack. On the other hand, if the jammer and scanner were on different nodes, surely the jammer would perform its attack. And this is a flowchart for a normal attacker's routine. As we can see, CH is a hiding cost, and the lambda I bar is a connectivity damage for removing a node. Alpha is the probability of being caught, and delta is probability of a continuing attack. Based on the normal jammer's routine, we can get the total instantaneous payoff for a jammer. That is, if the jammer and a scanner are on the same node, the instantaneous payoff for a jammer is the expected hiding cost plus the expected future gain value. By rearranging this equation, the expression, we can get the following expression equals to the hiding cost plus the discounted future gain value. Let gamma equals to 1 minus alpha multiply delta. As we can see, in fact, gamma is a probability for a jammer to continue its attack. So the value of gamma should be in between 0 and 1, and it is also one of the sufficient conditions for stochastic stochastic game to converge. And on the other hand, when jammer and the scanner are on different nodes, the jammer gets instantaneous payoff lambda I bar, which is a connectivity damage for removing a node.
So, wait, so gamma is the probability that it didn't get caught and then chose to continue its attack.
Yes.
All right.
Yeah, because alpha is a probability of being not caught, and 1 minus alpha is called probability not being caught. Yeah, and the delta is the probability of continuing.
Just the words for gamma are almost the same as the words for delta.
Yeah.
All right.
And the gamma is a quite important factor for stochastic game to converge. Is a discounted factor here. And in fact, lambda I bar can be any matrix. We use two matrices that are related with connectivity. The first one is connectivity of remaining graph after removing a node. As previously, we plug in SNR into our Laplacian matrix, and we get the fit value of a remaining graph according to this optimization. And the second one is throughput of a remaining graph after removing a node. As we can see, lambda I bar equals to the total throughput on the all remaining links by removing node I and the edges incident on node I. As we can see in this equation, J shouldn't equals to I. So it means that one node is removed from the network. So if we assume a payoff of scanner equals to the payoff of a jammer, this recursively played zero-sum game can be considered as a stochastic game shown as the following n by n matrix. As we can see, the entries of the diagonal corresponding to the instantaneous payoff when the scanner and the jammer are on different node, and the entries in the diagonal corresponding to the payoff of a jammer and the scanner when they are on the same node. As we can see here, game is replayed with discounted factor gamma. So why we call it a stochastic game? It is because game is replayed and based on the previous game status and the chosen strategy of a scanner and a jammer, which means the jammer and scanner has to be on the same node here. And also PI means the scanning strategy for scanner scan node I, and the QJ is a jamming strategy for jammer to jam node I, and N is the total number of nodes in the network. As we can see here, either scanner and or jammer can choose one out of N nodes to scan or to jam. Because it is a zero-sum game and it is with a discounted factor, so the game value can be uniquely defined by the following equations, assuming lambda I is in ascending order. If we are given the appropriate hiding cost, the game value V gamma can be found by the bisection search method. And this is the best strategy for game G gamma, and as we can see, if the sum of hiding costs is bounded by the connectivity threshold, we can get the mixed strategy for both jammer and the scanner. And this is a strategy for the scanner, and this is a strategy for the jammer. And they all in the probability form. And this indicates how much time a jammer spent on each node. So this is a simulation result on connectivity, and we can see with gamma becomes larger, the jammer tends to reallocate resources for a new attack. And also interestingly, the best strategy of a jammer is in a reverse order of that scanner. That means the jammer is trying to avoid the scanner's scan. So the next question is, what is the best strategy for a scanner if a jammer is motivated by different types of attack? For example, connectivity or throughput attack. So my heuristic here is that the ultimate goal of a jammer is to speed up the process of completing attack, since the longer his jamming attack, the more cost he will suffer. So I come up an expected jamming time before a successful attack. It is expressed by the following equations. By using this expected jamming time, we I give an example of comparing a connectivity and a throughput attack. The relationship between connectivity and the throughput attack can be formulated by the following 2x2 game matrix. As we can see, C is a connectivity attack, T is throughput attack. As we can see here, jammer is trying to minimize its jamming time. And by applying game theory tools, I get the best strategies to defend against the different category of jamming games. And this is an example of scenario where there's a 6-node network shown in the left picture, and we only ask node 2 to increase its transmission power. And this is the simulation result is shown on the right-hand side, and we can see a scanner should first defend against the connectivity attack if attacker has low probability gamma to continue its attack. And also, as transmission power of legitimate node increases, the scanner should switch to defend against the throughput attack.
One quick question.
Oh yeah.
How would your findings generalize if you have more than one jammer?
Oh, here we only consider for one jammer case here. So for multiple jammers, it will be over future work. Maybe probably by the multiple dimension matrix, game matrix, to describe the behavior of a jammer and the interaction of a jammer and the scanners like those. Do I answer your question?
Can't you analyze of just having one jammer but with modified parameters? Would that be a way to analyze that? Having multiple jammers.
Yes, this can be also a possible case if the multiple jammers they have a independent impact on the network connectivity, and if they are the impact can be the sum of individual attackers. Like so, yeah, it's kind of like a linear sum adding. Part of impacts equals to the total impacts. Of course, it needs some assumptions on the attack models for multiple attackers in here. And so let's come to the last project I did. This is also my future direction. It is apply artificial intelligence to connectivity study. There are several possible directions listed in my thesis to apply AI to study connectivity. One is multi-agent reinforcement learning. The other is a topology analysis with machine learning. And the last is learning dynamical data of network by game theory. Today, I will mainly talk about multi-agent reinforcement learning, and I will give a case study which demonstrates how to use multi-agent reinforcement learning to design intelligent transportation system in order to reduce congestions. So let's first go overview of multi-agent reinforcement learning. As we know, in a multi-reinforcement learning scenario, each agent performs a reinforcement learning algorithm in a network scenario, and an agent can either selfishly learn its own environment, which is in fact a zero-sum game, or it can collaboratively learn to achieve a common goal, which is in fact a positive-sum game. And because it is a positive-sum game, it encourages a future cooperation. As we know, the payoff of a collaborative learning should be larger than the payoff of selfish learning. And this is an overview of a Q-learning for one agent. As we can see in this picture, an agent takes action to the environment, and the environment gives a feedback reward to the agent. After the agent got the reward, it updates its status and also the Q value, and it will choose the optimal future actions based on the criteria that's to maximize the sum of the expected discounted rewards, and this process iterates until the Q value converges. So what is the challenge of using multi-agent reinforcement learning in a network scenario? As we know, the convergence of multi-agent reinforcement learning needs an agent to know all agents' actions in order to obtain the joint optimal policy. It is unrealistic for a network, especially a large-scale networks. However, we can achieve optimal decision if the following two conditions are satisfied. One is the global reward function should be linear, which means it is factorizable to the local reward function in a distributed fashion. And another condition is that the important interactions of an agent with other agents are limited within a small group. That means the agent itself only exchange informations with mainly exchange its informations with its neighbors. So here is the example demonstrate how to use a multi-agent reinforcement learning to design a traffic light control system in order to reduce congestion. This is also my internship work when I was in Fujitsu American Research Lab. So why we study congestions in traffic light system? Because congestions causes unusability of a road, and also, as we can see, congestion is a natural disturbance or interference forced by traffic network. So the question is, can we adapt infrastructure to improve the robust operation of the transportation system? Here, my achievement is I reduce the congestion in transportation system by multi-agent reinforcement learning through coordinating waiting queue lengths of vehicles and non-motorized vehicles. And this is a design of states in the queue learning algorithm. And S is the state. As we can see, S is composed by two components. One is the queue length for incoming cars, another is a queue length for incoming pedestrians. And this is a design of action set. As we know, for different types of intersections, the action set should be different. As we can see for this example, the cross-shape intersections, it has 8 actions in the action set. And at each time slot, only one action is taken in order to guarantee no collisions in the intersection, which also complies to the current traffic rules. And also, here is another example for the T-shaped intersection, and we can see there are 3 actions in the action set. So the probability for each action equals to the number of action AI taken divided by the total number of actions taken in the time period. As we know, as t approaches to infinity, according to the law of large numbers, this numerical results will converge to the real probability value. And this is an immediate cause rewards design for the queue learning. This is also the most important part to design a multi-reinforcement learning. So as we can see, at intersection I, the local reward is linear, and the total network reward equals to the sum of all the local rewards at each intersections. So it means that the total rewards is divisible into the local rewards. So it guarantees one of the conditions for the multi-agent, for the convergence of multi-agent reinforcement learning. And we can also see the local reward is composed by 2 components. One is the average incoming queue length, and the second one is the average total vehicle queue length at neighbors, which also include outgoing traffic from the intersection itself to the neighbors. It means that we don't want to release more cars to the neighbors if the neighbor already has a congestion. And the third part is the average pedestrian queue length. And as we can see, the calculation of local rewards needs knowing the traffic information of its neighbors. So it needs the message exchange between its neighbors. And so we ask nodes in the network to collaboratively broadcast the local traffic conditions to one-hop neighbors. As we can see in this picture, T is a... yes.
Question.
Do you have safety?
Yes, it will comes in the following slides. Yeah. So, as we can see, the T, which is the average queue length of all its neighbors, is exchanged among all one-hop neighbors. And in this table, we can see, for example, node I obtains the information T and the optimal actions from its neighbors, node 2 and node 3 and node 4. Although we can see the information is exchanged among one-hop neighbors, the information, in fact, can propagate to multi-hops to achieve a global optimal. So we also modified our algorithm in order to include the real-world constraints to protect the safety of pedestrians. As we can see, there are a bunch of ways to do that in order to comply to current traffic rules. And also, this is another constraint.
Go back.
Okay.
Can you give those in English? Like,
Yeah, I don't see.
what is a typical safety constraint? Like, don't cross when the traffic is coming at you, or what? I mean, give it to us in English instead of math.
Yeah. For this one, it means that if the northwest traffic light was green, and it shouldn't suddenly turns to left shouldn't suddenly turn the left traffic light to green, so that it guarantees pedestrian doesn't hurt when they are on the road like those.
Can you go back a couple slides to the actual picture you have, like a roadway, like?
For example, for this one, for this action, it shouldn't directly followed by these actions. This is a compliance. We wanted to realize the traffic rules. For example, if there's a pedestrian walking across this road when in this direction, it shouldn't suddenly change to when it turns to the left, so the pedestrian won't hurt when it is on this crossing area.
So, all right, so I can understand that in English again. If in the previous state there's a chance that a pedestrian could be crossing the road, you're not going to go into the next state where traffic would have come and possibly hit that guy.
Yes.
All right.
Is this typical way to model it? I would have somehow assumed that you have some sort of metric on how likely are accidents happening or something in those lines. But essentially you have constraints on what are acceptable behaviors for the lights.
Yes.
But you don't have a model on, well, if we do it this way, there will be 1,000 deaths per year, or something those lines.
Yes,
So that's not included.
Yes. This is we haven't collected those safety metrics to measure our algorithm here. This is a weakness, and this is our weakness, and we will do it in the future. And also it kind of in our simulation, we still haven't figured out how to collect the data of accidents on the road like those.
So how did you come up with these safety constraints? Are they given to you by, I don't know, township regulations or Department of Transportation regulations? Because what he's saying is, well, did you come up with these regulations based upon numbers that say that people crossing this way should not cross that way because people are stupid and they'll get smacked? What? I mean, how did you come up with these rules?
These rules are according to the current transportation rules. And it's also, we observe the intersections, the railroad intersections, and we found in the reality, like some action shouldn't follow another actions, like those. It is also we observed from the reality.
Okay.
So maybe we didn't list all of the cases, but we want to reduce the accident as much as possible, and it is also at some times complies to the real world constraint and the traffic rules like those.
Yeah, I understand this makes a lot of sense, but I was just wondering because it's not explicit there in the model that the amount of accidents.
Yes.
So I'll just follow up. So it's do you know why in the United States you are allowed to turn right on a red light? The reason is that this was modeled some decades ago, and people misunderstood the meaning of statistical significance. So actually, more people, pedestrians, die when you are allowed to turn right on red light, but people didn't understand the results because they settled too few, and one state followed, one or two states made this law, and all other states followed later, and now it's law of the land.
Yeah, right. This is a good suggestion. Yeah. Good.
Now it's good.
Yeah. Okay. It was stuck.
The laptop is frozen.
Yeah.
Oh no.
Escape.
You got a cursor. It is a 29 meg file, by the way.
Yeah. It's large file. When I upload it into my email, it comes to the normal. Yes. And this is also the constraint for pedestrian in the intersection. And the presence of the pedestrian can be detected by the civilian camera. And as we can see, Q-learning only changes its actions when no pedestrian in the intersection. So the actions change. So the new actions was taken in several time slots. And this is how we implement safety constraints in our Q-learning code. And we can see both these two constraints are implemented in the Q-learning action choices. And this is our simulation scenario, and we implemented our algorithm in an area of Sunnyvale of California. And the left picture is downloaded from OpenStreetMap, and we convert this map into the topology shown in the left. And as we can see, there are 33 traffic lights in the network, and we install our algorithm in these 33 traffic lights. And the traffic data is from California Department of Transportation, and we convert this traffic data into the average arriving rate for pedestrian and vehicles. Here, the average arriving rate for vehicle is 98 vehicles per minute, and for pedestrians, it is 60 pedestrians per minute.
That's a lot of people.
Yeah, a lot of people. Because we want to check our algorithm, the performance on reducing the pedestrian queue length. This is a main difference of our project to other current projects.
So,
Go ahead.
these numbers look insane.
Yeah.
So where do they measure them?
Yes.
Like,
Yeah.
are these cars or feet or what is it?
What are the units?
Units for the time is the seconds.
Sure, but vehicle queue length is it feet or?
Vehicle queue length is number of vehicles like this. It's not a meter. It's just the count, the number in that.
Waiting at one stoplight?
Yeah.
So 256,000 cars.
Oh, it's some of all the time slots, the waiting queue of time slots. So I haven't divided it by
The amount of time slots.
Yeah, I haven't divided the amount of time slots. So it's a sum of all the queue, some of the time slots for here. Yeah, yes.
I knew California was getting congested, but man,
Yes.
if they solve
Yeah,
that
yeah.
problem, they won't fall in the ocean.
Yeah. Yeah.
Right, next time, we should put in the normalization.
Yeah, normalization in here. Yes. Yeah.
Divided by 327.
Yeah, that would still be a
How many
lot.
time slots was it?
It's 4,500.
4,500.
Yeah, 4,500 times.
Still a lot of
Yeah,
cars.
a lot of cars.
Yeah.
But she was doing cars at 98 cars per minute, so she was,
And it's also a sum
Fast
of
forward traffic.
and also it's a sum of all the intersections, the waiting queue of all the intersections.
Oh,
It's not
so
just,
sorry.
just per intersection. It's
Alright.
not per intersection.
so you're integrating over
and
space
space.
and you're integrating over time.
Yeah.
Right, that's the type of thing we should include.
Okay. Next time I will correct this. Yes.
Next time.
Well, in all honesty, the advisor didn't catch that.
Yeah.
He was too enamored with the video that's gonna happen.
Oh, cool.
Yeah, and the first row is corresponding to our algorithm, and the last 4 rows corresponding to the algorithm that was implemented in the current transportation system. As we can see, it reduces both the vehicle and the pedestrian queue length, and also their waiting time. And also it reduces the pollution, the environmental pollution also. And this is a plot based on the previous table data, and we can see our algorithm has the lowest queue length and the waiting time, and also the pollution here.
Go back.
Oh, back. This
Travel, it doesn't affect the travel time though, because they're still traveling however much they travel, right?
Yeah.
Right.
And this is a video demo for our project. And the left simulation is corresponding to our algorithm, and the right simulation is a sensor case which currently implemented in the transportation system. And we want to compare the traffic conditions for the same intersections side by side. As we can see, those moving yellow dots are the vehicle cars, and those blue dots are the pedestrians. As we can see for the sensor case, there are already constructions in here. And for our case, on the left-hand side, the traffic goes very smoothly. And also the simulation collects the real-time data for the trip waiting time in the highlighted blue here. And we can see, then we can see our algorithm is less than, the value is less than the average trip waiting time is less than the current sensor case average trip time.
Which is underneath Priceline.com.
Sorry.
Yeah, I was
I-
it's sponsoring your talk.
Yeah, your advisor would like some of that sponsor funds if Priceline's paying.
Maybe.
It's okay. We believe you. We believe you.
Okay. Yeah.
So I have a question here.
Yes.
I've been wondering, where should you be? So what are the potential ripple effects of optimization? So let's say you optimize there the route 18 that I get to US1 from Bush campus, which I would like to get at 5 p.m. in 15 minutes instead of 35 minutes. They have to. So if you optimize something locally, what are the potential ripple effects for the whole grid? So, any ideas?
Yeah, here we do the message exchange between neighbors, so we consider the neighboring intersections, and we want to achieve the global optimal by exchange of message.
What is global? What is global in your case?
Global.
Yeah.
Global
It's
metric.
global in the spatial domain, but not in the temporal domain, right? Because
Not
your
temporal.
decision lab will lead to
What
Yeah.
is your space?
what?
How do you define global?
Well, in this
It's-
time slot
it's
across
the-
all the intersections as well.
Over the entire Sunnyvale, California, total queue length at all intersections integrated over all time.
Yes.
Well, that was her metric.
Yeah, this is
So that was offline.
Well, that's what
Optimization.
she recorded afterwards to show like that how it's reduced things.
yeah.
But then at a certain
But-
time slot, your knowledge is only
Yeah.
limited. You don't know what's happening in the future.
Yes.
Yes.
So it's only like a 2-hop.
Yeah, but it's
Exchange.
based on the historical traffic data. The Q-learning learns the traffic model based on the historical experience like those. So the kind of the data has to be stationary in some certain time period like those.
Well, I guess, let me rephrase. I wonder how so predictable like this. So like I make the same changes there that rotating a US1 might that incur something that people in Metatchen are getting screwed or something along those lines.
Yeah, the impact of the information or the congestion for the Q-learning, it decreases with the number of hops like length.
Okay.
Yeah, so if you are in distance very far from the current congested intersection, you won't be affected by this congestion because the impact decreases for example, gamma to the power of what, like those.
I think what Yanni is trying to ultimately get at is you can optimize for some metrics whereby you make the overall system as an aggregate do better, but you've really screwed up some sub-community that's not quite as important to the overall score. For example,
Yeah.
we can really optimize Route 1 because most of New Jersey traffic goes up and down Route 1. But in the process of it, you know what, that little side road over here in North Brunswick, its actual average waiting time now is 3 hours because we've backed traffic over there or something.
Yeah.
But most of the people in New Jersey, 98%, are living fine because now so these are the type of repercussions I think he was asking about.
Yeah, another possible solution I was thinking for that is we can we can give some weight for the intersections. Those ways according to the usually the traffic conditions or how the people use those congestions when they traveling like those, and then we do the corresponding Q learning according to those weights, and and to get maybe more appropriate global optimal like those.
I have also a question. How do you initialize how many vehicles are on the road? Is it a fixed number for every street, or you just randomly drop vehicles on this area?
Initialize what?
For example, in your demonstration, did you assume on every street initially the same vehicle density, or you had 2,000 cars and dropped it randomly on the streets of this area?
Yes, the mobility model is the arriving rate is from the Poisson distribution, and so for this area they have the same arriving rate for each road like here, because after we get the traffic data from California Department of Transportation, it kind of very hard to allocate it exactly on each specific node how the traffic should be. And also for the simulation part of the API, when they generate the trip, it only has the functions for the Poisson distribution. So here we add all the traffic informations and divided it by the area by the area for the location area, and get the revenue rate for each unit areas like those. And in future, yes, we will for more assign the more accurate traffic information on each road like those.
And if you think that the main roads will be much more congested than the
of course,
roads
yes.
and PS of the same density.
Allocate the traffic information on each specific road, because here it's like you got a topology of a graph, and you try to assign each weight on the link, and then this corresponding to optimization. For example, you can formulate an optimization equation for that, and it's kind of like, yeah, it's sometimes it's sometimes it's not more than polynomial complexity. So maybe we are thinking about how to efficiently allocate it. Probably currently we can just manually allocate it by for example, the probability, the how many portions the traffic data allocated to this road, and how many proportion of the traffic light allocate to that road. It kind of like we must first figure out which road is the more heavy road. Like, yeah, for example, like Route 1 is more heavy than usually the rural area road like those. So it's, yeah, this is quite a good question. It's, yeah, we are trying to figure it out now. Like those. Yeah.
Okay, we should move on.
Okay. Okay, let's go like this, because it cannot be full screen
No,
currently.
it's fine. It just disappeared.
Oh, good. Yes.
Now go back to slideshow.
So as we can see here, although my simulation is not ended, it was interrupted, and we can see it in the highlighted blue. This is a real data we calculate in real time, and we can see our algorithm has a less waiting time than the current sensor case algorithm. And so to sum up my work, I studied the problem of how wireless communication networks can be made robust when facing disturbances. I did the following 4 main contributions. One is the overlay design for network robustness. Another is discover adversarials and design topology for robust networks. And the third one is understand connectivity with interference. And the fourth one is defend against unknown attack strategies. And this is the references I used in my presentation. And this is my paper that is already published and submitted. And thank you for all of your attentions. If you have any questions, please ask.
So we'll start with asking questions from the audience. And if the audience has any questions.
One question just about your reactions to different throughput attacks and the connectivity attacks. You said you have 2 different reactions, 2 different responses. How do you see those 2 responses to be correlated? Do you consider them independent, or they are somehow correlated? because apparently when you increase the transmission power of one node to protect that node against connectivity attack, somehow you increase the throughput of the links connected to that node. So do you have the joint objective function in your response, or you just consider independent?
Yeah. In fact, these two metrics, they kind of they are different from each other, but they kind of overlap with each other also. And we in our theoretical starting part, we are trying to obtain these two metrics. Trying to combine these two metrics. And so it means that we apply the throughput into our connectivity, the field value calculations. And then we can check if the connectivity existed, what the throughput will be like those. So it's in the theoretical understanding part. And for how to compare them in separately, and we use the game theory here in order to check what's the when they are different, how the a jammer will choose which a scanner choose which strategy to attack for connectivity and throughput. Yeah.
You consider the effects of throughput also. And the next question is about you select a subset of nodes based on the lambda, you say, to just increase the connectivity of your network. I'm wondering, when one node is attacked for connectivity, do you also consider one reaction maybe to develop a new route, because you said some nodes, some links do not satisfy the threshold to be considered in your initial topology?
Yeah,
maybe by increasing a little transmission power of those nodes, the cost of developing is like a new route.
Yes.
Maybe lower than protecting that targeted node itself.
Yes, you are correct. Yes. In our protocol design, like adjusting the transmission power in physical layer, in that scenario, we consider a jammer block one node, and we increase the node based on the remaining graph after the jammer block delete one node from the topology. So the routing protocol will find a new route that was working around those areas, not across these areas. Yeah.
Can you go to slide 23?
23?
Yes.
Okay. Yes, this one. Here.
Is this so you are increasing the transmission power level?
Yes, this one.
And you are not putting any constraints, right? You are not putting any cost for increasing the transmission power level, right?
Yeah.
I mean, when you have some nodes, okay, and you are trying to cope with the attack, they have to increase their transmission power level, right? But you don't put any cost for increasing the transmission power level.
Oh yes, here. Oh yes, you are right. And here, for our case, there's no attacker here. It's just each node automatically allocates its transmission power. But your question is right. If your attacker remove one node, if we increase its power, we have to consider its cost, right? Yeah, cost of increase the connectivity. Yes, in fact, in our game theory part, for the lambda I bar, the matrix here, in our simulation, we also did the simulation that when the one node was removed, and if we increase the transmission power, we will add the cost of transmission power on the matrix, in the matrix level lambda I in the game theory part. Yes, we also simulation for that, and the simulation results has same trend as if we only consider the connectivity part. Yes, we did other papers that consider the cost of increasing the transmission power.
Any other questions from the audience? Otherwise, we need to go to closed session.
Thank you for coming.
Thank you, everyone, for attending. Thank you. I'd also, before everyone goes, I'd also like to, wait, Andre, I'd also like to thank Andre, who stepped in and helped advise Ying through different parts of the work, in particular on some of the game theory work. So.
Thank you.
All right.
We're going to ask you questions. So actually on the throughput stuff, what do you mean with throughput connectivity? I understand what is throughput and connectivity, but I completely missed that. What throughput connectivity means.
Throughput connectivity is that if there's a throughput on the link, well, we will consider a link exists in a topology graph.
Say it again, you missed a word in your sentence. If the throughput is, to the equation, if
It's
it's,
a channel theory, like, the SNMR is larger than the threshold.
there, larger than a threshold.